Okay, so how many ways are there to arrange the 3 girls in the middle? Well, this is just going to be 3 factorial. This is because 3 factorial ways to arrange the 3 girls, because you have to arrange them in a line. Now, for the boys on the outside over here, there are just going to be 2 factorial ways to arrange them. You can either have the first boy on the left and the second boy on the right, or the second boy on the left and the first boy on the right. So their final answer would just be 3 factorial times 2 factorial, which is equal to 6 times 2, which is 12. Okay, so do you have any questions on this problem? Okay, and then now I'm going to move on, and we're going to review some of the homework problems from last week. There was a school with 12 students. How many different ways are there to award the gold, silver, and bronze medal if no ties are possible? So let's let the gold medal be here, the silver be here, and the bronze be here. So this is the gold medalist, this is the silver, and this is the bronze. So of course, there are just going to be 12 choices for who can be the gold medalist because there are 12 students. Now, there are only 11 students left. So there are 11 choices for who can be the silver medalist. Now after that, there are 2 students are gone. So now there are only 10 students left. So there are 10 choices for the bronze medalist. And this will just have a product of, since 12 times 11 is 132, and 132 times 10 is 1320. So the number of ways to give a gold, silver, and bronze medal to 12 students is 1320. Now, another way to do this is with a permutation formula. And as you can see here, we have 3 distinct positions. We have 3 distinct positions, the gold, silver, and bronze. So we essentially are just evaluating P 12, 3. And this, by the permutation formula, if this is just going to be N, and this will be K, so this is equal to 12 factorial over 12 minus 3 factorial, which is equal to 12 factorial over 9 factorial, which is equal to 12 times 11 times 10, which is, again, the same answer as before, since 12 times 11 is 132, and 132 times 10 is 1320. So our answer is 1320. Now, if you have any questions, you can put them in the chat, but I'll move on to the next problem. And there was a very common mistake on this problem. How many ways are there to choose 4 balls from back, which contains 9 balls of different color? And again, the key word here, choose. As I saw the homework responses, a lot of people actually forgot to implement the choosing fact. And they just did 9 times 8 times 7 times 6. And they forgot that we're actually choosing and not permuting. And make sure you be on the lookout for these key words, because otherwise you might actually apply the wrong formula. And since it's choosing, we must use a choosing formula instead of just permuting them, because order does not matter in this case. So this is just going to be 9 choose 4, which is equal to 9 times 8 times 8 times 7 times 6 times 5 factorial over 5 factorial times 4 factorial. Actually, sorry, I skipped steps there, so let me just redo that. So this is actually going to be 9 factorial, 9 minus 4 factorial, 4 factorial, which is equal to 9 factorial, 5 factorial times 4 factorial, which is equal to 9 times 8 times 7 times 6 times 5 factorial, divided by 5 factorial times 4 factorial. And then these terms will cancel, and we are left with 9 times 8 times 7 times 6 divided by 24. And these will cancel, and we get an answer of 126. Okay, so now I'm going to move on to the next problem. So how many integers between 1000 and 9999 have 4 distinct? Remember, this means digits have to be different digits. So again, let's have 4 slots. So again, for the first slot, we can have any number between 1 and 9. Let's just say we chose 5, for example. Then there will be 9 choices for this slot. And now for this next digit over here, typically we could have any number between 0 and 9. But since we've already used the 5, we only have 9 numbers left. So there will again be 9 choices for the second digit right here. And let's just, for example, again, assume it's 2, for example. Now for this next digit over here, you can have anything again from 0 to 9. But again, excluding the 5 and the 2, because those are the first and second digits. And we must have distinct digits, so they must be different. And make sure in many problems to pay attention to the key wording of the problem, because that can sometimes distinguish which formula or which concept to use in which case. So again, there are going to be 8 choices for this digit right here. Again, and then let's just say, for example, it's a 3, let's say. And now for this final digit, it can be anything from 0 to 9 again, except it can't be 5, 2, or 3, because we already chose them for the first 3 digits. Therefore, there will be 7 choices for this last digit here, and we can assume it's 1 maybe. And so our answer would just be the product of all these terms. And this is equal to 81, because 9 times 9, and times 56, which is equal to 4536. This is our final answer right here for this problem. Now let's look at this problem. Many people thought that this problem was slightly confusing worded, so I'll explain this. So Mrs. Jones is organizing a potluck and wants to serve 8 different dishes. Each family can bring 3 dishes. How many families can Mrs. Jones invite so that no 2 families bring the same on the lookout for keywords, combination. Remember the choosing, that means we have to use choosing probably, something to do along those lines. Same combination of dishes. Okay, so we have the 8 different dishes, and we need to bring 3 dishes. So let's just say we have 8 different families, or sorry, 8 different dishes. So let's say one family brings the dish combination of 1, 2, and 3. So all 3 of these dishes. And now let's say another family brings 1, 2, and 4. And now what about if another family brings the same combination of dishes, 1, 2, and 3? But then that's not allowed, because it says that no 2 families can bring the same combination of dishes. So if we have 2 families that both bring this combination 1, 2, and 3, that would not be allowed. So that would actually be incorrect. So we cannot have 2 same families with the same 3 dishes chosen. So therefore, the maximum number of ways to choose 3 dishes from these 8 dishes, well, the maximum number of families that can be there such that no two families bring the same 3 dishes, that will just be 8 choose 3. And this is because that with every 3 dishes chosen, you can only have 1 family for every 3 dishes chosen. Because if you have a duplicate, that would not be allowed. You can evaluate this. It's just 8 factorial over 8 minus 3 factorial. 8 minus 3 factorial times 3 factorial, which is equal to 8 factorial over 5 factorial times 3 factorial, which is 8 times 7 times 6 times 5 factorial over 5 factorial times 3 factorial, and 5 factorials cancel, and 6 is also 3 factorial, so these will also cancel, and we are left with 56 as our answer. Okay, now let's try this last problem over here. We already did this problem in class, and the answer was 156,160. And if you're looking for the solution again, you can always go back and rewatch the sections of last week's video. If you're looking to review the solution of this. And now we'll go to number 6. How many arrangements of the word bottle are there such that the 2 T's and the O's remain together? Okay, so let's write out all the letters of bottle. B, O, T, T, L, and E. And we are given the problem that the 2 T's and the O's must remain together. So let's circle them right here. These letters must remain together. So let's just call it some group. So I'm going to rewrite the letters over here. B, and has to be together, so let's call it G because it's a group of 3 letters, L, and E. And how many ways are there to arrange this? Well, there are 4 letters, so it's just going to be 4 factorial. And now, we also must arrange the 3 letters inside the group, O, T, and T. And again, if you remember the formula for the number of ways to arrange a word, just n factorial over d1 factorial times d2 factorial times d3 factorial, and so on. And since there are 3 letters, it's going to be 3 factorial. But notice there are 2 t's, so we must divide by 2 factorial. And this would just be 3 times 2 factorial over 2 factorial, which is 3. So we multiply this out, we get 4 factorial times 3, which is equal to 24 times 3, which is 72. Do any of you have any questions on any of this homework? Do you have any questions on this homework you can ask? Or if you had anything you want to clarify or anything? Or do you want me to explain anything again if you find it unclear? Okay. So just to highlight the key ideas of this problem, look at both the cases, look at the 2 T's and O's grouping, and then you see the other 3 letters. So they're going to just be 4 factorial, and then we can arrange the 3 O, T, and P in 3 ways. Okay, so now we're going to move on to today's topic. So today's topic is going to be casework. And casework is solving problems, counting or probability problems by considering the different cases and adding all of them together. So don't be afraid by this complicated thing, as I'll explain what this is with a simple example. So how many different combinations are there of $5 bills and $2 bills that can be used to make a total of $17? And in this problem, order does not matter. Okay, so let's look at the different cases. So of course, that's obvious that if you have 4 or more $5 bills, that's going to exceed the total of $17. So make sure, of course, there has to be at max 3 $5 bills, because if there's 4 or more, the total will exceed $20. So that's not even possible. So let's look at the 3 different cases. The first case is we have 3 $5 bills. And as you can see, the total has to be 17. And the total of the $5 bills right here is 15. So there is going to be $2 left. So since we can, how can we afford $2 with the $2 bills? Well, you can just simply add 2. Since 2 divided by 2 is 1, you can only have 1 $2 bills, and we get this case works. There's one way for this case, so let's just write 1 here. Now, what about the other case, when there's only 2 $5 bills? So let's say we have 2 right here, so 5 plus 5, let's say. And since the total again is $17, let's see how much we have left after we subtract the $10 we have. $5 bills. Well, then there's $7 left. And can anyone tell me whether it's possible to make $7 out of $2 bills?
No.
Okay, so I'm just going to explain it then. It's actually not possible because $7 from just $2 bills, 7 is odd. It's not divisible by 2. So there's no possible ways to form $7 from just $2 bills. So, of course, then we cannot have any $2 bills. So this case doesn't work. Now, what about the case when there's only 1 $5 bill, let's say? Then you're left with $12 because we have a total of $17, and we must subtract the $5 we already have. Now, we are left with just $12. So how many ways are there to make $12 with $2 bills? So let's think. So since 12 divided by 2 is 6, 6 $2 bills will make the total 17. So as you can see, that if you have 1 $5 bill, we are left with $12. So we must divide by 2, and we get that there will be 6. We get that there is going to be a total of 6 $2 bills to make the total equal to 17. So this again has one case that works. This works, and there's one way for this. And now let's see what happens when we have no $5 bills. So let's call it 0. Then there's just going to be $17 left. But then, as you can see, 17 is not divisible by 2 again. So we cannot form 17 from $2 bills. That's impossible, because 17 is odd. So it's not divisible by 2. And since 17 is not divisible by 2, it's not possible to make 17 with just $2 bills. So again, this case doesn't work. So what is the total answer for this problem? Well, we can either have 3 5s and a 2, which is one case, or we can have 1 5 and 6 2s, which is also one case. So what's the total? Well, that would just be 2. So that's the answer to this problem. There are 2 different combinations. Remember, combinations means no order. The order does not matter. So like, for example, having the $2 bill here or here, you don't have to worry about any of that. So our answer would just be 2. So make sure you understand this, and if you have any questions, you can either ask them directly or type it in the chat. I'll give you and make sure you understand the part about how we can take it in different cases by the number of $5 bills. Okay, then I'm going to move on to make sure you understand how exactly we just broke it up into different cases. And we're going to use the same exact strategy for this another AMC 8 problem. Okay, so the middle school 8 basketball conference has 8 teams. Every season, each team plays every other conference team twice. And also, each team also plays 4 games against non-conference opponents. So what is the total number of games that are played in a season involving the middle school 8 teams? Okay, so let's let the 8 teams be 1, 2, 3, 4, 5, 6, 7, or 8. So let's first count the number of games between this own conference themselves. So it says that each season, that every team plays every other conference team twice. So since each team plays every other conference team twice, we must choose how many pairs of 2 teams there are from these 8 people. So does anybody know how many pairs of 2 teams are there from all of these 8 people? You can type in the chat, or you can say it. You can do whatever you want. So just to rephrase the question, so essentially you have to choose 2 teams to play each other. So you can, for example, choose 1 and 2, 2 and 3, 3 and 4. And how many ways are there to choose 2 teams to play each other? Try to put your best guess. Even if you get it wrong, that's okay. And remember, please send all PMs to Sohail Rocky and not the Sohail, because I won't be checking the messages on Sohail. So send all your messages to Sohail Rocky instead of just Sohail. So let's look at the number of ways to choose 2 teams from all these 8 teams. Well, we can choose 2 teams to play each other. We have 8 teams. We choose 2 teams out of 8. So just 8 choose 2. Make sure you understand why this is true. Because we choose out of the 8 teams, in order to choose 2 that are going to play each other, we can choose, like, for example, we can just do 8 choose 2. Since there's 8 teams, and we must choose 2 of them to play with each other. So just 8 choose 2. Make sure you understand why this is true, because it's very important. Okay, so now the problem says that each team plays every other conference team twice. Since we play every other conference team twice, we multiply by 2, of course. And this is just, we can do 8 choose 2, which is 8 factorial over 8 minus 2 factorial times 2 factorial, and again, this times 2 is there, which is equal to 8 factorial over 6 factorial, 2 times 2 factorial times 2, which is 8 times 7 times 6 factorial over 2 factorial, or 6 factorial times 2 factorial. And these will both cancel, and you're left with 8 times 7 divided by 2, which is equal to 8 times 7 is 56, and 56 divided by 2 is 28. 28, but then we also have to multiply by 2, so it's going to be 28 times 2. Since again, remember, plays every other conference team twice. So since because we have to play every other conference team twice, we multiply by 2 and we get an answer of 56. But that's not our final answer. That's only one case. Now the problem also says that we play 4 games against non-conference opponents. So since we must play against non-conference opponents, how many ways are there to do this? Well, each of the 8 teams plays 4 times against other non-conference opponents. So how many ways are there to do this? Well, there are 8 teams, and each team plays 4 additional games against non-conference opponents. And this is a total of 32 games from the middle school A conference and the non-conference opponents. So the total answer would just be 56 plus 32, which is equal to 88. And remember, the key ideas from this problem is that first we found the number of ways that each team plays every other conference team twice. This would just be 8 choose 2 times 2. Since there's 2 ways to choose 2 teams to play against each other, and each team plays twice against other people. And then the second case is also going to be 8 times 4, since each team plays 4 games against non-conference opponents. Okay, so if you have any questions, feel free to ask them. You can put them in the chat or speak them out loud. Do whatever, and I'll try to answer them if you have any. So I'll wait for about 10 to 15 more seconds. Okay, so remember the key ideas, 2 cases. In general, you can always think of some problems can be broken up into some cases, and you can evaluate the number of ways in each of the cases and just add them up. So now I'm going to move on to this next problem right here. So how many pairs of parallel edges are there, such as AB, which is this, AB just basically means this right here, or GH, EH, and FG the cube has. Okay, so I'm just going to highlight some edges right here. So we can think of the edges in several pairs. So let's first look at these edges right here that I'm going to be marking in blue. So as you can see, these 4 edges that are marked in blue over here, they're all parallel, because this is parallel to this is parallel, AE is parallel to BF, and DH is parallel to DH right here. For example, DH is parallel to CG, and similarly CG is parallel to BF, and they're all parallel to each other. So it's asking for the number of pairs of parallel edges. So as you can see, these 4 edges right here. So again, there's 4 edges here, and you must find a pair of them to be parallel. Does anybody know how many ways are there to choose a pair or parallel edges from all of these 4 edges? I'll give you a hint for this one. It's something to do with choosing, because we have to find a pair of edges. Okay, so I'm going to give a hint here. So there are 4 edges. There are 4 edges right here, and you must choose a pair of them, so 2 of them. So there are 4 edges, we choose 2 of them. Well, that's just 4, choose 2. And similarly, and I'm going to evaluate this here, 4 choose 2 is 4 factorial, over 4 minus 2 factorial, times 2 factorial, which is equal to 4 factorial over 2 factorial times 2 factorial, which is 4 times 3 times 2 factorial over 2 factorial times 2 factorial, and these terms will both cancel, and then we are left with 4 times 3 divided by 2, and 4 times 3 is 12, 12 divided by 2 is 6. So 4 choose 2 is 6. But we're not done yet. We've only looked at these 4 edges, AE, BF, DH, and CG. Now we might also have to look at some other edges. For example, AD, EH, BC, and FG. And as you can see, these edges that I've labeled with orange, all 4 of these edges are also parallel. So we can choose a pair of them to be parallel as well. And that's, again, just 4 choose 2. Choose 2, which is equal to 6. So again, for the blue lines that I've marked, there's going to be 6 choices for 2 parallel edges. And again, for the same thing for the orange lines. And finally, let's look at these red lines right here. As you can see, these red edges I'm marking over here, they have the same property as the blue and orange edges. We can choose any of two of them to be parallel. So just like earlier, it's just going to be 4 choose 2 is equal to 6 for the red edges as well. So therefore, our total is just going to be 6 times 3, or 4 choose 2 times 3, which is 6 times 3. Because, as you can think about it, all 4 of these edges are parallel, and you choose 2 of them. You can choose 2 of them to actually be a pair. Make sure pair just means 2. So it's just going to be 4 choose 2 times 3, which is 6 times 3. It gives us an answer of 18 for this problem. And this, in fact, at first, you might think of it as a geometry problem. But really, it's just a counting problem because you're trying to find the number of pairs of edges. So again, remember the key ideas to take away from this problem are that we have all these parallel edges and try to group them. I mean, of course, you could have just listed them all out, but that would take a longer time. So again, if you have any questions, please feel free to put them in the chat or just ask them out loud. And you can see all 4 of these edges, all 4 of the blue edges, all 4 of the orange edges, all 4 of the red edges. You choose any 2 of those groups of colors of edges, and they're going to be parallel. So again, ask your question. If you have any questions, please ask them. Okay, so now I'm going to move on to the next example. Something weird is happening. Sorry. So now we're going to look at complementary counting. Complementary counting is a problem-solving technique counting the opposite of what we want, subtracting that from the total number of cases. So don't worry about the definition here. I'm going to demonstrate this with an example. So if you toss 4 coins, how many ways will there be at least 1 head? So generally for complementary counting problems, these words at least, typically at least means complementary counting is probably what you want to use for the problem. So at least, make sure you remember that at least, if you see at least in a problem, think maybe you should use complementary counting. So let me demonstrate this technique. If you toss 4 coins, in how many ways will there be at least 1 head? So let's just say these 4 coin flips are. So let's try to count the opposite of what we want. Does anybody know what the opposite of having at least 1 head is?
0 heads.
Well, if there's at least 1 head, there can either be 1, 2, 3, or 4 heads. And we could just use Casework to count that, but that would take a lot of time. So what's the opposite of that? If there's not 1, 2, 3, or 4 heads, how many heads are there?
0 heads.
There's not 1. So if there's 1, 2, 3, 4 heads, so what's the only thing that we've left out? The only thing we've left out is if there's 0 heads. So if there's 1, 2, 3, or 4 heads, then there will be at least 1 head. But if there's 0 heads, there will not be at least 1 head. So again, we're trying to do complementary counting here. So we're trying to count the number of ways. We're trying to count the number of counting the opposite. So we're trying to count the opposite of what we want. So how many ways are there to have 0 heads when you toss 4 coins? So let the 4 coin flips be given by these 3 slots. If there's 0 heads and 4 coins, there's going to be 4 tails. So all 4 of these will have to be tails. So there's one way for this. But now what about if there is 1 head? Now what are the total number of ways to toss the 4 coins? We have these 4 coin flips right here. And each of them can either be a tail or a head. A tail or a head. And again, because it's complementary counting, we want to subtract this opposite from the total number of ways. So how many total coin flips are there? Since there's 2 choices for each of these coin flips, the product is just going to be 2 to the 4, which is 16. Because each flip can either be a tails or a head. We have 16 for this case. And since we want the number of ways where there's at least 1 head, and we found the number of ways where there are at least 0, where there are 0 heads, we must subtract that off. And we can do this very easily. We get 16 minus 1, which is 15. So again, the key ideas are that you how many ways there such that there's the opposite, and the number of ways such that there are a total number of ways to flip 4 coins, such that with the outcomes. So you subtract the number of ways where there are 0 heads from the total possible outcomes of 4 coin flips. So again, the total coin flips is 16, and the number of ways where there's no heads is 1. So we subtract that off to get 15. So do you have any questions on this problem? This technique is very powerful, and rather than doing a lot of casework, this can really help simplify things greatly. Okay, so I think I'm going to move on to this next problem here. This is very similar. If you tossed 4 coins, in how many ways will there be at least 2 heads? So again, at least. Make sure you remember that at least. At least means that we use complementary counting. This should just be like, you should just know that, oh, at least probably is a sign that complementary counting is what I should use. So again, let's find what the complement is. So does anybody know what, you can put in the chat if you want, what is the opposite of having at least 2 heads? So what's the opposite of having at least 2 heads? Yeah, exactly, having 0 or 1 heads. So let's count the number of ways to have 0 or 1 heads. And again, we could have just done this by direct casework, finding the number of ways that we can have 2, 3, or 4 heads, but that's harder. So let's find the number of ways where we have 0 or 1 heads. So what if we have 0 heads? Then all coin flips must be tails, right? Because if there's 0 heads, there are 4 tails. There is just one way for this. Now for the other case. What if there's 1 head? Well then there are 4 slots again. There are 4 possible coin flips. And then we have 4 total coins, and we must choose 1 of them to be head and 3 of them to be tails. So for example, this could be head, and these could all be tails. So how many ways are there to choose the 1 head position out of all 4 positions? Well, the 1 head, out of the 4 positions, you must choose 1 of them to be heads. So it's just going to be 4 choose 1, which is just 4. So again, now we use complementary counting. And this is a step that many people sometimes forget, is that when you use complementary counting, our final answer is not just 5, 1 plus 4. Because we counted the opposite. So now we subtract it from the total number of coin flips. So let's find the total number of ways we found it here. As we found here, the total number of coin flips from 4 coins is just 16. So our final answer would actually be 16, the total number of ways, minus 1, minus 4. Because these are number of ways to have 0 or 1 heads, to not have at least 2 heads, to have less than 2 heads. So this will just be 11. This is the final answer for this problem. So do you have any questions on this problem?
No.
Make sure we just found the opposite. When there's 0 heads, 1 head. This is just going to be 1. This will just be 4, and we subtract that off from our total. So complementary counting can really simplify problems a lot, which is why it's a very powerful technique. So again, yeah, just put your questions in the chat or say them out loud. Okay, so I think now we're ready to move on to this next problem here, which is again another complementary counting problem. How many 3-digit numbers have at least 2 digits that are the same? So I'm going to give a minute to let you try and solve this problem on your own. So as a hint, use complementary counting. So the first, let's find the total number of 3-digit numbers. Minus 3-digit numbers with all the digits distinct. So try to use complementary counting to actually get an answer from this problem. I'm going to continue with the solution at okay, so now I'm going to present the solution to this problem. So let's first find the total number of three-digit numbers. So first of all, how many numbers are less than 1,000? Well, you can have anything from, you can have anything from 1 to 999. So there are going to be 999 numbers less than 1,000. But then out of these numbers, there are going to be 99 numbers from 1 to 99 that are two-digit numbers. So there are 99 of these possible two-digit numbers. So we want the number of three-digit numbers. So we subtract this off. And then we do this and we get that there are 900 three-digit numbers. And the three-digit numbers are from 100 to 999. So since the three-digit numbers range from 100 to 999, so there are 900 total three-digit numbers. Now, if you remember from last week, as we did this problem, there are 648 three-digit numbers. And we can do this because there are 3 slots, and there are the first digit can be anything from 1 to 9, next digit is 0 to 9, and 0 to 9. And there are 9 choices for this, and after that, 1 digit is already used up, and there are 9 digits, 9 choices for this, and after that, 2 digits are used up. So there are 8 choices for this. That gives a total of 648. And right now I briefly explained it, but if you're interested in more detailed explanation on how we got 648, we went over this last class. You can always just check out the recording for that as well. So then we use complementary counting again. So there are 900 total three-digit numbers, and there are 648 three-digit numbers which are all the same digits. Therefore, since at least 2 digits that are the same is the opposite of having all three digits different or distinct. So our answer would just be 900 minus 648, which is 252. So make sure you understand how we can use complementary counting and apply them to these sorts of problems. Subtract the complement from the total. So the complement is basically the opposite. So you can use these same ideas for a variety of problems. Okay, I think we're ready to move on now. Okay, so now we're going to learn a new concept called OverCounting. OverCounting is a process of counting more than what you need and then systematically subtracting the parts which do not belong. So we count more than what you need, and then subtract the parts that don't belong. Let's take a look at this problem to demonstrate what we actually mean. So how many positive numbers less than or equal to 100 are multiples of 2 or 3? So let's consider this in a Venn diagram point of view. So let this here be the multiples of 2. And let this over here be the multiples of 3. So let's first find the number of multiples of 2. So the number of multiples of 2 is just going to be 100 divided by 2. This is going to be 50, because there are going to be a multiple of 2 every 2 numbers. So there's 50 multiples of 2. And now we find the number of multiples of 3. Well, this would just be 100 divided by 3, which is 33, and has a remainder of 1, but we don't care about the remainder because we're looking for integer multiples. So the remainder we can just completely ignore. It does not matter at all. So there are 50 multiples of 2, and there's 33 multiples of 3. But then, what if a number, for example, like 6? 6 is both a multiple of 2 or 3. So we counted it, when we were counting the number of multiples of 2, we also counted it with the number of multiples of 3. So we counted 6 in both of these cases already. We already counted 6. So we're overcounting 6, hence the name of this term here. We overcounted the multiples of 2 and 3, but we overcounted the multiples of 6. So the multiples of 6 right here, so the multiples of 6, we are overcounting them. So because we're overcounting it, we have to subtract it off from our total count. So we have to subtract off the number of multiples of 6. And how many multiples of 6 are there? Well, again, we just do 100 divided by 6. Is 16. And again, we can completely ignore the remainder because that's not an integer multiple. So there are going to be 16 multiples of 6. So because we are overcounting the multiples of 6, we subtract it from our total. And as you can see with the Venn diagram over here, the total number of multiples of 2 or 3 will just be the number of multiples of 2, which is 50, plus the number of multiples of 3, which is 33, minus the number of multiples of 6, because you're overcounting that. So this gives us 83 minus 16, which is 67. So there are 67 numbers, positive numbers, less than 100, less than or equal to 100, that are multiples of 2 or 3. So now let's try a very simple follow-up question. How many positive numbers less than or equal to 100 are not multiples of 2 or 3? So as we found here, there are 67 multiples of 2 or 3. So in order for it to not be a multiple of 2 or 3, we must subtract the multiples of 2 or 3 from the total number of numbers. And clearly, there are 100 numbers less than or equal to 100, positive numbers. But then there are 67 numbers that are multiples of 2 or 3. So there are 33 numbers that are not multiple of 2 or 3. So our answer for this problem is 33. Make sure you understand both of these problems and how we use the Venn diagram to approach this problem. And again, we have overcounting, which is the process of subtracting it out. So make sure to count, make sure to think about you're actually counting, and make sure there are no duplicates, and we subtract those duplicates off. And that's pretty much what overcounting is. Okay, so I'm going to now move on to example 9. And I'm going to let you guys try this problem on your own. So out of 200 students, there are 100 taking geometry, 70 taking algebra, and 30 taking both. How many students are taking neither? So okay, let's think about this problem with the Venn diagram again. So there's 200 total students. Let's call this problem here geometry. Try this work on this problem on your own as well. This is geometry, this is algebra. So how many students are taking neither? So the number of students taking neither are going to be 200, since that's the total, minus the number of students in both geometry and algebra. So I'll give you till 349 to work on this problem, or 350. So I'm going to give you another hint to get you moving a little more forward. So there are, again, 100 students taking geometry, 70 taking algebra, and there are 30 taking both. So let's first find the number of students in both of these bubbles combined, both of these circles, in all these circles. So there are 100 students taking geometry, 70 students taking algebra. But then we're overcounting the number of students who are taking both. So we're overcounting this region over here. We're overcounting this middle section here. Because the middle section here, we counting the number of students who took both geometry and algebra. So we subtract 30. This gives us 140 students taking either geometry or algebra. But now we want to find the students taking neither geometry or algebra. So we subtract this from the total. There are 200 total students, minus 140 students taking geometry or algebra. This gives us 60 students are taking neither algebra nor geometry. So 60 is the answer to this problem here. So make sure you understand how you get this answer to this problem. We subtract it out and we found the total number of students, subtracted it from the geometry and algebra, and then we added back to both because those are the intersection of both the geometry and the algebra. Now I'll move on to this tricky problem again. So Mr. Sanders has 3 grandchildren who calls her regularly. One calls every 3 days, one every 4 days, and one every 5 days. And all 3 called on December 31st, 2016. How many days in the next year did she not receive a phone call from any of her grandchildren? So again, let's draw a Venn diagram to make it easy to understand. So let's call this circle here the number of students who took both, the number of the grandchildren who called her every 3 days. Something weird is happening with the undo. And for this next bubble, the one who took it every 4 days. And this one, the one who called her every 5 days. So since there are 365 days in a year, since 2017, the year after this is not a leap year, so there are 365 days. So how many students are there? This is a very tricky problem before I move in. It's basically the same thing that we did here, except we have to do it for 3 things. So there's 365 days in 2017. So during this next year, so this first grandchild over here is called by 365 by 3, which is equal to 121. Because every 3 days, she's called by the first grandchild. Now for this one with 4 days, she's called 365 divided by 4, which is equal to 91. Because every 4 days, she's called by this grandchild. Now for this 5th day, she's called 365 divided by 5, which is equal to 73. Because there's 73 times that she's called by this 5th grandchild. Called by the grandchild who calls her every 5 days. But now, just like earlier, you're overcounting this area right here. And also here, and this whole area is being overcounted, as you can see. This whole area we're already counting twice, so that's not good because these areas are already being overcounted. So we have to subtract them off. So let's first find the number of ways that both her grandchildren call 3 and 4 to 5 days, let's say. So so in order for them to both call every 3 and 5 days, they must call every 15 days. And this is because on the days that are multiples of 3, the grandchild who calls every 3 days is being called. Now, for the days that are multiples of 5, the grandchild who calls every 5 days is being called. So in order for them both to be called on the same day, they must have a multiple of 15. So there are 365 divided by 15, which is equal to 20. So this is equal to 30 for example. The number of ways this is just going to be 365 divided by 15, which is just going to be 24. Make sure you understand that when a grandchild calls every 3 days and 5 days, it's the same as both of them be called every 15th day, because 15 is like multiple of 3 and 5, both. And now every 3 days and every 4 days, same thing as you do for the 3 and 5. Every third day and fourth day that the grandchild calls, this will be for every 12th day instead. So this will be 365. I was going to write it over here, I guess. 365, since that's the number of days in 2017, divided by 12, because every 12th day she's called by both the grandchild who calls every 3 and every 4 days. And this will just be 30. Now, what about for the grandchild, 2 grandchildren who call every 4 days and every 5 days? Well, again, in order to call every 4 days and 5 days, you need to call every 20 days. Both of them call every 20 days. Because the first one calls every 4 days, the second one calls every 5 days. So they both call cumulatively every 20 days. So therefore, the number of ways in their both calls is going to be 365 divided by 20, which is equal to 18. But then now let's look at this middle section over here. So in the beginning, we counted this middle section in 3 days. We again counted it into 4 days. And we again counted it into 5 days. But then when we were subtracted it when we counted both 3 and 5 days. And we subtracted it when we counted the 4 and 5 days and 3 and 4 days. So we subtracted it in all 3 of these. But then again, we counted it 3 times, we subtracted it 3 times. So now we're left with it being counted 0 times. So now this region is actually undercounted. And since this region is undercounted, we must add it back. And since it's being counted every 3, 4, and 5 days, so this is going to be a multiple of 3, 4, and 5. In order to be a multiple of 3, 4, and 5, it's going to have to be a multiple of 60. In order to be a multiple of 3 and 4 days and 5 days, the multiple of 3 and 4 is 12, and the multiple of 12 and 5 is 60. In order to be called every 3, 4, and 5 days, it needs to be called every 60 days. And this 365 divided by 60 is equal to 6. This is because in order to be called every 3, 4, and 5 days, it needs to be called every 60 days. So we must add back this region over here because we're undercounting it. We're not counting it at all. So we must add it back. So it needs to be called every 3, 4, and 5 days. It needs to be called every 60 days. So therefore, 365 divided by 60 equals to 6 is what we have to add back. So now, in order to find our final answer, we just do 121 plus 91 plus 73. And then again, we must subtract 24 because it's the number of times both the 3 and the 4 grandchild calls. And let me just mark it here. It's 24 right here. This is going to be this region. This 120 is one where it's about 4 days and 5 days, which is there. And the 3 and 4 is just going to be right there. So these are the regions, and we must find the total. And again, this last thing over here is going to be right here. Our final answer is just going to be 365, 121, plus 91, plus 73. And then we subtract off 30, plus 18, plus 24. These are the totals over here, here, and here. So these are the totals in each of the 3 and 4 days, 4 and 5 days, 3 and 5 days. We must subtract off these totals. And then again, we must add back this total because we're undercounting it actually. And then we add this back, we get 6. And this actually evaluates to 219 if you add it up. I'm not going to add it up. I'm pretty sure you can do that on your own. But then we remember, now we also use some kind of a complementary counting technique as well. There are 365 days in a year. And it's asking how many days she did not receive a phone call from any of her grandchildren. So 365, the total number of days in a year, minus 219, the days when she gets called by at least one of her 3 grandchildren. Well, this is just going to be 365 minus 219. And this actually is 146. This is a very complicated problem, as you can see here. So this is I'm going to summarize the things that are in this problem here. So 3 and 4 days. So first we found the number of times in these regions over here. We found this region, and then we found it in this region as well. And then we also found it for this region. We subtracted it for this region, and this region. And then we have to re-add it back for this region. And this is a very tricky idea at first. So count the number of ways in this area, and then we must subtract it off. And then for the final thing over here, we've already counted it 3 times. And we subtracted it 3 times in these 3 regions over here. And then we must add it back one more time, because the number of days where all 3 of the grandchildren called still counts as being called by at least one of the grandchildren. Therefore, we just evaluate this, as you can see over here. This will just be this expression here. And we get that there's 219 ways. We subtract that from the total of 365 days. We get 146 ways. Okay, so this was a little bit tricky problem, so make sure you understand how it works. But now, if you want to review the solution to this problem, you can rewatch the video. Make sure you understand how you get this. So now we're going to skip probability because there's not enough time left. And these are the homework problems. I will edit them and remove some of the problems because they were probability related and we did not have enough time to cover probability. So we'll go over that next week in the beginning of next class. And so if you have any last questions, feel free to ask them. Otherwise, make sure, again, just like last week, I'll send out a submission form for the homework problems. I might change them up a bit. It's not what you're actually going to be doing for now. And then after that, I'll send you the handout as well, and you can review the video solutions. And I highly recommend that you all review the video for the parts that you didn't understand, and maybe even try solving some of the problems that I went over again, just to make sure you have a proper understanding of these concepts, because for all these complicated concepts, 1 hour is very little to actually explain them all and have a good understanding of them. So I highly recommend you rewatch the video, rewatch parts of the video, and attempt the homework problems to the best of your ability. And don't, again, just like this class, I will go over the homework problems from this week next week. Okay then, see you next class. Bye everyone.
Thank you. Bye.
Thank you.
Bye.
Thank you. Bye.